Hello, good afternoon or good evening. Many thanks, Yijun, for the kind presentation. My name is Marco Veltri. I will be continuing on the work that was presented by my colleague in the previous session, as demonstrated the workflow for a durability analysis with dynamic loading obtained in via Adams. In fact, we learned about fatigue and durability while doing fatigue analysis, and we demonstrated, as I mentioned, this process of going from a finite element to produce a flexible part that can then be accessed by the multi-body dynamic system. And then we stopped right short of passing the information with regard to the loads to the fatigue code, which is what we're going to be doing tonight. If you haven't seen this presentation, please take your time after the show to go to that, to follow the link and complete your session with that interesting presentation. So, we did have particular focus on the flexible body capability of atoms, and in fact, we also demonstrated some of the key features of a durability plugin which sits inside Adams, which is called, in fact, Adams Durability. Today, as for session 2, we're going to rekindle a bit some of the concepts with regard to fatigue and durability, and we're going to place fatigue also within the CAE environment. And we're going to introduce very quickly some of the key capabilities of our flagship product for fatigue that is called MSC Fatigue, which is going to be used for the demo. Then we're going to be going into the demo itself and closing the loop, the durability loop, and learning how to set up a fatigue analysis. And we're going to have particular specific focus on duty cycle methods. We're going to have some conclusion and then some time, hopefully, for questions and answers. Now, this wouldn't be a fatigue presentation if we didn't have a picture of August Wöhler, the so-called father of fatigue. It was already in 1850, around 1850, that Wöhler stated that material can be induced to fail by many repetitions of stresses, all of which are lower than the static strength. This is the most fundamental concept for fatigue analysis. Over the years, of course, there have been lots of development, research, and scientists all applied to the topic of fatigue, but the fundamental proposition still remain the necessity of an empirical relationship between the applied fluctuating cycles of stress and the repeats that can be obtained through these cycles. So this is nicely represented by the stress life curves, which is quite often associated to fatigue analysis. So the concept of the key concept in fatigue is therefore to identify the material. This is pointed out by the green arrow, and the relationship between stress amplitudes and cycles that can be obtained at a given amplitude, but also to determine the loads. The blue arrow, this is what Adams provides, accuracy with regard to the loads. Of course, this could also be done experimentally, but at a much higher cost. So the fatigue code intervened in taking those two models to predict, in fact, the fatigue analysis. How this is done? This is the basic workflow for any fatigue product based on finite element analysis. You will have to the left here a starting point with system loads. This can be simulated or acquired experimentally. The system loads will be cascaded down to component level. And for each one of the nodes or entities we will want to recover the stresses and perform fatigue analysis, we will perform a rainflow cycle counting process that collects every loading cycle that is experienced locally by the component. Using SN or similar curve, we can calculate the damage accrued by each cycle and accumulate with every other cycle via linear damage summation rule. Summing all the damage for each node then results in the beautiful plots, for example, the half fatigue life. the concepts are well understood, but obviously it's very important that the user experience and the capacity to for the user to seamlessly pass information from different tools that are used in the CAE arena. You can see here that you would have FE codes such as Nastran, Abacus, or Mark, and ANSYS and so on, or you will have multi-body dynamic solvers or system analysis and control system, and they all need to be connected strongly. And of course, the fatigue product should be in the loop and not in a dead end as a sort of a post-processing exercise. In fact, MSC Fatigue is a bit special in that sense because it sits inside Patran, so it's entirely within an FE GUI environment. In case you are not familiar with MSC Fatigue, let's just say that MSC Fatigue, or P-Fatigue as it was called back then in the late 80s, was the very first commercial finite element fatigue solver. So it has over 20 years of successful industrial deployment. It comprises, it's a very complete product, obviously, so it comprises SN, EN, solvers, back propagation, capability for vibration analysis, sign sweep, deterministic sign sweep analysis, or random analysis. It can also, of course, address vertically with some specific module the problem of Welds, spot Welds or seam Welds, which is something very, very specific and very fundamental in a lot of applications, especially in automotive systems. And there are also other specialist tools. Important to mention is that currently there is a cut-down version of Patran that is available for non-Patran customers that are willing to use MSC Fatigue. So when we mention MSC Fatigue, we like to stress the fact that MSC Fatigue is an integrated FE and MBS fatigue design solver. And in fact, the diagram shown here shows how the connection and how the workflow with the other players in the CAE arena works. You have input to the left, shown here to the left. This includes the material information, the loading that is often extracted from atoms, as we have seen during the session one, and the geometry and finite element description of the part. The results, therefore, the analysis options are vary and depend on the kind of method that you are selected. Often, the most common method are obviously the stress life and the strain life method. Then to the right, you see some possible plots, fringe plots data, but also some localized sensitivity analysis or distribution of damage and other type of fatigue-specific plots. So, why is then a benefit to be inside an FE, a full-blown FE pre- and post-processor such as Patran? Well, of course, you can access the loads from atoms, of course, that is given. But the most important issue here is that when you have certain level of complexity in your model, for example, if we go back to the wind turbine example, in this particular component, you would have, in a wing component, a blade component, you would have 400 and more groups, as many properties, and as many materials. This means basically that you have a lot of different layers of information groups that you have to move yourself around, and also multiple integration, Gauss points, layers, element orientation, normals. If you are not inside a finite element environment, you'll be struggling to provide good, make sense of your fatigue analysis. And so, if you've not seen fatigue before, or Patran, if you've not seen Patran lately, this is what Patran 2011 looks like. And now, obviously, we are in the latest release, 2012.2. We have a completely new look and feel, and with the so-called ribbonized window system. And among all the tabs that you are normally finding in any pre and post finite element products, such as load and boundary condition, meshing, and visualization of results, we also have a durability tab, which is specific, of course, for MSC. And the high level of integration within the Patran GUI results in a very powerful interactive method of analysis for fatigue. and also very state-of-the-art pre and post-processing capabilities of Patran are utilized fully by MSC Fatigue. And then, of course, there would be also some very specific additional post-processing capabilities that are part of the Fatigue product itself. So very briefly, and let me close for this part of the presentation by mentioning some very key features of the new version of Patran 2012 of Fatigue 2012.2. First of all, as of 2011, we have completely replaced a large part of our Fatigue solver. So this means that in collaboration with ENCODE, our partners for development of Fatigue products ever since the experience of P-Fatigue, we have added to the existing capability, which can be represented here with the pink box. We have added the additional capabilities, the blue box, and we have replaced some legacy capabilities. We also have some additional features that are that have been extended from by MSC directly. All this to provide really the most complete state-of-the-art Fatigue package out there. So once again, just this is not going to cover all the features. This is just going to give you some ideas of what you're going to find in 2012. We have the new GUIs for material databases and for duty cycle analysis. So this is just a snippet. And then we have a new solver for sign sweep analysis, a GUI that is 64-bit, but also a solver that is 64-bit, so the capacity to analyze large models. We have also a possibility to simultaneously activate multiple threads, which is basically parallel processing, and this makes obviously fatigue analysis much quicker. We have more robust EN and SN solvers, enhanced SimWell capabilities, and we're going to look through this demonstration now to explore the new duty cycle capabilities, which are going to be very useful for demonstration. Okay, so this was a very quick run-through. Please do inquire more specific about MSC Fatigue if I was able to make you a bit curious. And now let's dive into the live demo. And just allow me to remind you, to rekindle a bit the previous session. What the process that we're trying to follow is one of starting from finite element analysis, generating, of course, the component and the model shape of this component. The model shape I've used because we want to provide a reduced stiffness model to atoms, and so that atoms can conveniently calculate the participation of each of these modes to the analysis, and then MSC Fatigue at the end of this loop can superimpose the model participation to reobtain the stress history and perform very computational intensive fatigue analysis at very computational low computational cost. So the prequel of this exercise is really the calculation of the mode shape. I'm going to just not to leave any stone unturned, and just going to briefly express what the principal model superposition is and how MSC Nastran and Adams, or well, any other solver, FE solver should do that, but in this exercise we're going to be using Nastran to calculate the mode shape. Those are expressed under a light blue shading. The mode shape are given to, or stiffness of the mode shape are given to Nastran, to Adams, that will be sold in the model coordinates. So how much each one of these shapes will be participating in during the analysis. So the model shape, the model coordinate can be seen as a sort of a scale factor for a particular mode. And the result of the Adams simulation is, of course, the time history of the model coordinates. And this is what we're going to be passing on to MSC Fatigue in order to produce this superposition exercise. So, in fact, let's just remind ourselves what we went through during the first session. We imported an Adams model of an ATV vehicle. We then imported a flexible left to lower control arm. So we could obviously repeat this kind of process for every flexible part that we want to integrate into our system. We modified the damping on the flexible part. We did some animations, and we ran the dynamic simulation. Now we're going to retrace this analysis by starting at step 6, where we review the results in Adams, and then we do some bit of playing with Adams durability and export the results to MSC Fatigue, so that we can then start the fatigue analysis. Okay, so let me get out of the PowerPoint and into Adams. Okay, so the famous ATV vehicle is here represented. I'm going to play the animation that, or at least part of the animation that was shown during the first session. As you can see, most of this model is rigid, composed of rigid parts, but you can see here something going on in terms of shading. In fact, this is the max principal stress that is being shown, and the reason why we can show stresses inside Adams is because we have imported a flexible component from a finite element analysis through a Modal inertial file. Now, the important capability here that we're using is our durability plugin, which is a specific plugin to dialog with fatigue code. Let's just exploit an important capability here. That is the capability to identify the most critical location during the fatigue during the dynamic analysis. So we're going to identify the flexible body that we want to search for hotspots, and we point at available analysis, that is the last run. And one thing we're going to be doing, we're going to look for maximum principal stresses, maximum principal stresses, and within a radius of 40 millimeters. What that means is that basically we're not going to, once we found a certain hotspot area, we're going to look beyond 40 millimeters for another hotspot, so that we don't condense all the hotspots in one single area. So this is already, before even doing fatigue analysis, we already know that node 88258 is going to experience the most the highest maximum principal at time step after 5 seconds, and the maximum stress would be around 140 megapascal. So with this information, perhaps what we could do then is create a hotspot nodal plot. So we'll be using once again the durability plugin, and I've basically already prepared the exercise here. We are pointing out, we provide the nodes that we want to find out, for which we want to express from FE-MBS max principal and mean principal, and then we look for the plot. Interestingly here, what I'm showing here, I'm going to animate this thing again. What we're showing here on the plot is we have selected 3 model participation for mode 7, 8, and 9, and just to show how the model shapes the participation function are really time history. So they don't have units; they just multiply the model stresses or the model deformation to basically identify how much mode is participating at each moment in time. So if we stop the animation once again, we go back into the nodal plot, we can look at this very briefly. We can visualize what is happening on node 88258. You can see here we have simultaneously showing max principal and mean principal. Okay, this is very important for fatigue analysis because more often than not, we'll be using the max absolute principal as a fatigue criterion. So as a lookup stress value, we don't use a tensor, obviously, we use a scalar value, and we using to look up the SN curve, we'll be using the max principal when the maximum absolute value is higher than the mean principal, and vice versa. In this area here, you can see where the max principal is 0, the mean principal takes over. So the total excursion is from top of the max principal to the minimum of the lower principal. So if we plot the von Mises, you can see that sometimes the von Mises could be misleading, because if we use von Mises for fatigue analysis, we'll be missing out on the compressive side, but also we'll be probably taking a bit of unfair advantage with regard to the maximum stress. Now, this is all we have time for, apart from maybe one last interesting capability here that we can point out to, is visualizing the hotspots directly on the component, which is always a nice capability. Once again, we're going to be expressing a certain distance, and you can see here how the various hotspots have been identified and on the component itself. It's also quite a nice feature to have. We can look at the node ID and their value and the time frame. Okay, so enough about durability plot. Let's export all these results into a file, and this is going to be used. So maybe I should go a bit slower. We're using, once again, durability plugin, MSC Fatigue export. We identify a certain flexible body. We only have one, so it's fairly easy. And then we give a job name, let's say delete, because we already have done this before, so we don't want to overcrowd. And we hit apply. What happens is that as soon as we export the model participation function, what we have is basically we had a total of 34 modes, so we expect a total of 34 model participation functions, and all these are going to be used to load our components in Fatigue. Okay, so let me just briefly go back to the PowerPoint to introduce what is coming next. First of all, we just seen one single event here, an hotspot table. In fact, I only showed 5 seconds. In reality, the full analysis lasts 60 seconds. In truth, more often than not, we'll be dealing with a number of events, and they all have to be accumulated in one single result. This is called duty cycle analysis. For example, here we have the hotspot table and the video relative to an out-of-phase bumps proving round. I'm going to move to the next possible example. This is a jump once again, and showing interestingly showing the relevant importance of max principle, mean principle, and compared to von Mises. You can see the peaks from the von Mises are a bit lower in this case than the max absolute principle. So this is just a couple of examples of additional events, but in truth we would have a schedule that comprises really probably 20 or even more events. So what we want to do to perform a fatigue analysis is establish a certain equivalent unit. So let's say that every 10,000 kilometers we expect 5,000 repetition of the 60-second sequence on the 4-poster rig. We expect a certain number of jumps, and we expect a certain number of out-of-phase bumps run, and a certain number of pitch. Okay, so let's try to represent this requirement into our fatigue product, and let's try to let's say, aim for a design life for the product of 200,000 kilometers. Okay, so we're going to enter now the last part of the demonstration, opening MSC Fatigue and showing a bit around MSC Fatigue and how to import the loads, how to generate a duty cycle agenda and run fatigue analysis with MSC Fatigue. We'll be importing the results and draw some conclusions. Okay, so let's get out of the presentation and back into FE codes. So this is the now famous lower control arm, and this environment here is Patran. For those who are not familiar with it, once again, we have now a system of ribbons that facilitate the access of all the features, the many feature Patran. And let's stick to the results very, very briefly, just to demonstrate that the fatigue, the model stresses are already here and available. I'm just going to show one single result, mode number 7. So we know that mode number 7 provides a certain level of stress that goes very high, and we need to know how much this stress is really activated by the dynamic analysis. This is what Adams has already done for us. So what we need to do is just combine all the model stresses by the actual loads. So let's enter the fatigue durability ribbon. And as you can see here on the top, we have a specific section dedicated to stress life, break initiation, macro, and other vertical tools. Let's pick up on the setup for stress analysis, for fatigue analysis using the stress life method. So let's look from the top of the fatigue module, the fatigue GUI, and you can see here that we can select the fatigue method that we want to use, in this case SN, and then we have result location, the results unit. We need to tell the code what units we're going to be using for our fatigue material description. And here we can switch between the classic and the DTlib, the new solver. So we're going to demonstrate the new solver today. I already have given a job name. So all we have to do is basically go through 3 simple steps. Once we have set up the general parameters that are common to all the analysis, you can see here I'm going to use all the processors that are available. And I'm going to also output max and mean stress, which is also an additional piece of information. It's quite useful. That's not bad at the moment with the other controllers. In terms of SN analysis, of course, I have multiple options. I can choose different types of material modeling. The standard SN curve, the one that we've seen during the presentation, it's the one that we're going to be using today, but we could be using more complex, more complicated material systems such as multiple mean curve, multiple R ratio curve, directly high diagram, and other options as well. So I've been already introducing, sort of pre-warning you about the selection of max absolute principles. So this has been clarified enough. And other possible selection are sign von Mises, or sign max shear, or critical plane. Let's again skip through the other additional settings that are not too important at this stage. So before we move into the loading section, which would be sort of the closure to this exercise, let's also connect the part that we want to analyze to a certain material information. Let me open a material database very briefly so that we can show off a bit the new material database. So this is just to demonstrate that we have a brand new C++ graphical interface. It already comes loaded with a large number of materials. And of course, it's completely open to add other materials. Now, I have shown here some special curves. Those are the British standard classes for Welds analysis. In fact, I'm actually going to be picking one of these curves just to sort of compensate for the fact that I haven't really discussed about Welds. But probably the most critical part of this component would be the Welds itself. So, in the material information form, what we're going to be doing is simply associate our part to a material. And the benefit of using Patran is, of course, that we have access to every possible group that is already existing. So you can see here I have already selected the Welds class, and here I have a number of groups that are readily available, and I already have prepared the stress output group that is going to be the subject of my fatigue analysis. Very useful capability also is that because we're going to have multiple layers, we want to analyze both layers at once. So we're going to analyze it in the top shell and the bottom shell at the same time. If I had more than one material, of course, all I needed to do is just add more rows and add more associations. But in our case, we only have one material. So we have selected a Welds material. We're going to leave untouched all the multiply, offset, and other possible capabilities that can be activated, and leave the defaults as they are. Now it's the time, therefore, to associate the loads that have been generated in Adams with the MSC Fatigue. And in order to do that, we're going to we have to first create our duty cycle schedule. So what it means is that we want to basically recreate that number repetition and event sequence. And to do that, we're going to use this brand new duty cycle interface. And here, to this empty sheet, we're going to have to add our events. So we're going to add time history events. We're going to browse through the directory where the Adams analysis is being performed. We scan for this directory, and we discover a certain number of events. You can recognize the delete that we just exported. We're not going to use that. That was just an example. But if I pick up on the ditch example, on the jump, on the out of phase bump, and the poster 60 seconds, then I can take all this in one single click. So each one of these really represents multiple channels, because each one of the events represents 34 loading channels. So if I expand momentarily, I can see that, for example, the ditch is associated with 34 channels, and so is the jump, and so is the out of phase and the poster. Okay, so I'm satisfied that the number of channels matches my number of modes, and I can now complete the durability agenda by the duty-cycle agenda, basically by associating the correct number of repetitions for each event. Let's say that we're going to have, for the sake of this example, 100 repeats each, 1,000 repeats, 1,000 jumps, maybe 100 out of phase section, and for each one of these events, we're going to have 5,000 of event post 60 seconds. And all this, we're going to save this into live duty. And now this agenda is stored in my directory. If I then go into the loading information form, you can see that I can browse and pick up on my newly generated duty cycle. All I need to do, as I have the duty cycle agenda, I have to express, I have to associate the correct number of loads. As you can see here, a bit like it happened with the material information form, I have expressed that I have 34 channels to associate. We can inquire the database to verify that we have, in fact, this loading available. And this 34 channels that have been exported by Adams find their match in 34 model stresses that are contained in my Patran database that have been provided through finite element analysis. So you can see here, you can verify that we have, and obviously everything is performed in one click as long as you have the field down toggle enabled, which I hadn't. So I'm going to do this again. Perfect. Okay, so this is really all. All you have to do now is take the time to run the analysis. It will take about 3 minutes, so I'm not going to do this live at the moment, but I can import the results of a previous analysis. And now that the results are available, we can browse through the standard result capability in Patran to visualize the fatigue results. So what we will see is that, for example, this last analysis would provide two different results, one for top and one for bottom. So I can look at the damage resulting from this analysis. And of course, the analysis, the results in terms of damage are not particularly interesting right away because there is so much difference within different parts. So normally what I would do, I would express results in form of log damage, and now the picture becomes a bit nicer. Because I had expressed also the results in form of equivalent units, which is in kilometers, each one of my duty cycle agenda was representative of 10,000 kilometers. I can look at the results in terms of kilometers as well. So I can, if I put the results in terms of kilometers in life, you will see that the lowest fatigue life here is about 100,000 kilometers, which is lower than what we were hoping for. And of course, this might be located in only a few restricted entities, so we can go and give a further look to verify whether we have really a problem or not. Another useful plot that you can get here are the max and the mean stresses, which are experienced throughout the analysis. So, of course, I've rushed a bit the post-processing part, but hopefully you get the picture. And another important part of the results output is also going on under my work directory, because if I go very briefly to the exercise, to the folder where my fatigue job has been run, you can see that I have alongside with all my duty cycle binary results, I also have a CSV file. So what the command separated file will give me is the possibility to browse to every single location and filter, for example, every location. Here, I'm looking at for example, the very first node that is being analyzed, 39495, and you can see here that for this node, I have a set of results. First of all, the one on the top is the bottom cumulative results from all the events, and then also the cumulative results from all on the top layer from all the events. But I can also single out each one of the events, top and bottom, and how much they have contributed in terms of damage to the overall damage. And if I change the filtering here and I plot the largest damage to smallest damage, you can see here that I have some interesting results showing that only, in fact, a couple of entities don't match my requirements. And what this means is that perhaps maybe this is a finite element modeling, not a real fatigue issue, or perhaps this is something that I can improve very quickly. Particularly, it was, as you can see here, the jump that is contributing mostly to the damage, and also the four-poster at one point reaches an interesting high level damage level. But altogether, this is not such a bad account. So with this, I think we can close the demo and go very briefly finish up with the presentation. So we have gone through a full loop from Adams, actually from finite element to Adams and then back to fatigue. And but the most important concept was remains that we need to get the loads right, and in order to be able to perform the right prediction. So the key aspect, therefore, is to perform very reliable durability analysis with the correct loads, and use of Adams and flexible bodies clearly helps this capability. The possibility to easily verify on the fly the durability effects of the model variation, which is allowed through the loop of an integrated product such as MSC Fatigue, brings bringing fatigue analysis upfront is therefore an invaluable benefit in the success of virtual product design. So sometimes it's not always possible to predict customer usage, but if you want to take things to the extreme, you can also analyze more rare events, such as the one that we just saw. Okay, so final comments. We've gone through a fairly realistic example of completely integrated virtual durability process. Modal superposition now has become sort of a standard, industrial standard to address dynamic simulation and fatigue. And MSC Fatigue completes your Adams durability loads and FE component stresses with state-of-the-art fatigue analysis solver. And problems that would be out of reach they would take literally weeks or months to solve can now be solved in a few hours. And with this, I think we can leave a bit of time for question and answer.